Hello, welcome to lecture 21 of the course. Having introduced the coherent states in the last class, in this lecture we are going to discuss coherent states of light in great details. Followed by this, we are going to discuss the squeeze states of light, which we are going to discuss in the context of a general harmonic oscillator. Let's begin. In the last class, we discussed how an external light field can be detected using a detector. In fact, we discussed about the photo detection process. It is simply the steps are like this. Say light, it may be a high intensity light, and even a low intensity light can also be detected, and for that generally photo cathode is used, and for high intensity beam photodiodes are used. So anyway, the process looks like this. Say light is incident on a photodetector, and this light interacts with the atoms in the photodetector, causing emission of electrons in the photodiode, and which results in the generation of current I of t. And by using appropriate electronics, this current is converted to a voltage signal, and measurement of this voltage signal gives the information about the intensity of the light which is incident. Okay, so that's how the detection process goes, and that's how a detector works. Then we consider two detectors, say D1 and D2, and we discussed about the joint probability of photo detection at these two detectors located at distance r1 and r2, and the joint probability was given by this expression. And at this stage we are talking about the classical, we are considering a semi-classical treatment here, and light is still considered to be in classical light. On the other hand, the detector, the atoms are obviously they are treated quantum mechanically, and this is the joint probability expression, and eta 1 and eta 2 are the efficiency of the detectors D1 and D2 respectively. Then we defined the so-called second order correlation function z of 2. This is the classical second order correlation function, which is basically the average of the product of the intensities measured at the detector at R1 and R2, and in terms of the corresponding electric fields, this second order correlation function can be written in this particular form. Now here only thing to be noted here is that the order and the manner in which these electric fields are written. So this is called normal ordering and time ordering. Then using this second order correlation function, this joint probability could be written in this particular form. Then we have discussed the so-called quantum second order correlation function. Now the electric field is considered quantum mechanically, so therefore electric fields are replaced by their corresponding operators. Okay, and rather than this second order correlation function, we are more interested in the normalized second order correlation function, and this is normalized with respect to the intensities, and then this normalized second order correlation function is written in this particular form, and it is dimensionless because it is normalized. And we have confined ourselves to the case when r1 is equal to r2 and t1 is equal to t2, and then replacing these electric field operators by their corresponding annihilation and creation operator. E plus is replaced by a annihilation operator, E minus is replaced by a dagger, the creation operator. Then we get this compact expression for the second order quantum second order correlation function, which can further be written in terms of the variance in the photon number delta n and the mean photon number n. And utilizing this expression, we have found out the photon number state. For photon number state, the second order correlation function was calculated to be like this. And also in this context, we discussed the case when the second order correlation function is less than 1, and it basically give rise to the phenomena of anti-correlation. That means the photons are now separated from each other, they don't group together. That's what it means when the z2 second order correlation function is less than 1. Then we discussed about thermal light, the second order correlation function, and we worked out that this is equal to 2.
By the way, let me make it clear that the second order correlation function is related to probability, but it is not exactly probability. So don't think that Z2 cannot be greater than 1. So as you have seen in the last class, that the second order correlation function for thermal light is 2, which means that the thermal photons are very strongly correlated to each other, and that gives rise to the phenomena of bunching as well. Then we also discussed the correlation function, second order correlation function we calculated for the coherent light or the Poissonian light, and it turns out to be simply equal to 1, and that means the photons in the coherent light are independent of each other. And we went on to discuss the coherent states of light, which is basically can be thought of as a, it's the coherent state is the eigenstate of the so-called annihilation operator, and it can be written in terms of the number state or the Fock state or the photon number state as a superposition of photon number states. Then we went on to calculate this its form, and we found that the coherent states can be written in this particular form, and I asked you to find out what is C0, and I told you that C0 can be worked out, and this would be simply equal to e to the power mod alpha square by 2, and I hope you have tried it. Now let me actually quickly do it for you. It's very trivial. You just have to use the fact that this coherent state is normalized. Let me use this normalization condition to find out this quantity C0. This kth alpha is equal to summation over n alpha to the power n divided by n factorial C0 kth n. So this bra alpha I can write, let me put another index, say m is equal to 0 to infinity, then it would be alpha star to the power m divided by square root of m factorial, and here I am going to have C0 star, and this would be bra m. So therefore now I have this quantity, this equation I can now write as, let me put these terms, m is equal to 0 to infinity, n is equal to 0 to infinity. Okay, then I have alpha star m divided by root over m factorial C0 star. Let me write everything first, and then from the kth alpha part I have alpha to the power n divided by square root of n factorial C0 kth n, right? So this is what I have now, and this is equal to 1, and now let me write it in this form: sum over m sum over n alpha star m alpha to the power n n factorial root over n factorial C0 mod square, and I have here mn. So as you can see, this guy is nothing but the Kronecker delta mn. So it is equal to 1 if m is equal to n. So I will be left out only with one summation n. So that's going to be alpha star m is equal to n now. So therefore it is mod alpha square to the power n. And here I have simply n factorial, right? And then I have C0 mod square is equal to 1. So now you see this quantity, I think you know that x to the power n by n factorial summation, this is nothing but e to the power x. So using this, you can immediately see, if you look at this term, so this term is nothing but e to the power mod alpha square, and then you have, it is multiplied by C0 mod square is equal to 1, and this means that C0 mod square is equal to e to the power minus mod alpha square, and this gives you C0 is equal to e to the power minus mod alpha square by 2. So you see, that's how you can find out what is C0, and therefore I have my coherent state. The expression for the coherent state is e to the power minus mod alpha square by 2 summation n is equal to 0 to infinity alpha to the power n divided by n factorial square root of n factorial ket n. So this is the expression for the coherent state. Now we can find out the probability of finding n photons in the field being in a coherent state quite easily. The probability of finding n photons in the coherent state Pn can be worked out by calculating the modulus of n, the scalar product of n alpha square will, okay, you know this, that this is going to give you the probability of finding n photons in the coherent state, because you know the expression for the coherent state which already you have worked out. So if you take the scalar product with ket alpha by n, then, and if you take the mod square, you are going to get this expression. It will be e to the power minus mod alpha square, and you will have modulus of alpha to the power twice n divided by n factorial. Now if you look at it, then you see that this is nothing but the it's a Poissonian distribution. Now what about the mean photon number? To do that, you just have to calculate the expectation value of the number operator in the coherent state. So mean photon number in the coherent state can also be very easily calculated, because you know that this number operator n cap is a dagger a, and you know that a when operates on alpha, so you know you have alpha is a number, complex number, then ket alpha, and also you know that when this bra alpha is operated by a dagger, then you are going to get alpha star bra alpha. So utilizing this, immediately you see that you are going to get it to be mod alpha square and scalar product of alpha alpha, because coherent state is normalized. So therefore you have the mean photon number in the coherent state is simply mod alpha square. Then at this stage, let me ask about the variance or the fluctuation of the electric field in the coherent state. To do that, we can do some calculations, very straightforward calculation. As you know that the variance in the electric field is given by the usual this formula, that we expectation value of E square minus the square of the expectation value of the electric field. Now we have to calculate these expectation values in the coherent state. For that we need to know the electric field operator, and we know that let me just take the case of the propagating wave. For the propagating wave, the electric field operator is given by I eta vector, where eta is the polarization direction. Then you have h cross omega divided by twice epsilon 0 v. V is the quantization volume, and we are taking a single mode electric field, and then we have this a e to the power I kz minus omega t minus a dagger e to the power minus I kz minus omega t. By the way, while I am writing it, please don't get confused, because earlier when I have written down this electric field operator for the propagating field, I have taken z is equal to 0, but now I am using the full expression. Now having this expression for the electric field, we can find out the expectation value of the electric field operator in the coherent state, and which is a very straightforwardly can be calculated. However, before I go on to do the calculation, let me introduce some useful parameters to simplify the calculation. Say E0 is equal to, let me take E0 as twice s cross omega divided by epsilon 0 v. I am going to put a square root here, and chi is equal to kz minus omega t. With this, I can now write expectation value of the electric field in the coherent state as I E0 by 2. I have alpha a e to the power I chi minus a dagger e to the power minus I chi alpha, and here you can easily see that I am going to get I E0 by 2. I will have alpha e to the power I chi minus alpha star e to the power minus I chi. Okay, and this is going to give me, I will have I E0 by 2, and if I take alpha is a complex quantity, if I take alpha as mod alpha e to the power I phi, phi is the phase of the coherent state, then I can write it as I E0 by 2 mod alpha e to the power I chi plus phi minus e to the power minus I chi plus phi. Okay, and this will result in, I will get it as mod alpha E0 sine, you will have, let me write the full expression now, chi is equal to kz minus omega t, then I have phi. Okay, so this is the expression for the electric field, expectation value of the electric field in the coherent state. This shows that the expectation value of the electric field is varying exactly like a classical electric field varies. Okay, and this is the reason why light field in the coherent state is said to be, it is actually in a quantum state which mimics the classical field of radiation most closely. Now you can go on to calculate the expectation value of E square in the coherent state. The calculation is straightforward but a little bit lengthy, and I urge you to do it yourself. If you do this calculation, then you are going to get the result. Maybe you will do this in the problem solving session. However, please do it yourself and show that expectation value of E square in the coherent state is going to be E0 square by 4, and you will have this expression here, 1 plus 4 mod alpha square sine square, you will have kz minus omega t plus phi. Okay, so this is what you should get, and therefore you can immediately get this variance in the electric field in the coherent state by putting the values of the expectation value of E square and expectation value of E, and then if you take the square and if you put it, then you are going to get simply, it would be E0 square by 4, and E0 square already we have taken to be square root of twice s cross omega by epsilon 0 v. So therefore we are going to get the whole thing as simply s cross omega by twice epsilon 0 v. And as you can see, these quantities are constant quantities, so, and it is, there is no time dependency is there. So this is basically what I have from here is that delta E, which is the standard deviation in the electric field in the coherent state, that is going to be square root of s cross omega by twice epsilon 0 v, and because this uncertainty is constant in time and it is independent, therefore it is a constant. Basically the standard deviation for the electric field in the coherent state is a constant. In fact, this can be more clearly shown by a plot here. Here in this plot we are plotting the expectation value of the electric field in the coherent state versus time. As you can see, the electric field is here varying sinusoidally, just like an electric field, classical electric field. Okay, this is how it is varying, but now this electric field has some width, and this width refers to the uncertainty, and that is equal to square root of s cross omega by twice epsilon 0 v, and this width is constant in time as it is can be seen from this plot. Apart from this uncertainty in the electric field, there is a basically uncertainty in the phase of the coherent state as well, which is also evident from the plot, but we are not calculating it. You can do it as an exercise to calculate this uncertainty as well. By the way, let me also mention here in this plot that we have taken z is equal to 0 and therefore the electric field expectation value here I am taking it as mod alpha E0 sine omega t minus plus phi. Okay, this is what I am taking, and delta E, as I already written, it is equal to square root of s cross omega by twice epsilon 0 v. Now many times instead of the electric field operator, the so-called quadrature operators are used, because the quadrature operators are dimensionless and it has deep physical meaning also and very useful. Let me introduce these quadrature operators. Two operators we are going to have. One is x. It is defined as a plus a dagger by 2, and another quadrature operator is y, that is a minus a dagger divided by 2y. So that's how the quadrature operators are defined. Now you can calculate the expectation value of this quadrature, say x in the coherent state. It's very easy to calculate the expectation value of the quadrature x in the coherent state. Is simply you have to calculate this quantity, and by definition you can easily work it out. Alpha here a plus a dagger alpha, and this is going to simply give you 1/2 alpha alpha star, and which is nothing but you have 1/2 twice of the real part of alpha, because alpha is a complex number. So this is going to give you simply real part of alpha. Otherwise you can also do one thing, because you remember that I have taken alpha as mod alpha e to the power I phi. So this is going to give me real alpha as mod alpha cos phi. Okay, again you can find out expectation value of x square in the coherent state, and that also very easily you can calculate. So you just have to operate on this gate alpha by the a plus a dagger twice, right? This, and therefore here you are going to have 1/4, and please do it yourself, and you should find mod alpha square cos square phi plus 1/4. Okay, please show it yourself, do it yourself, and therefore you can again find out the variance in the quadrature x, and that is going to be simply you just put the expressions that is worked out, and if you put it there, and you are going to get it as simply 1/4. And this means that the standard deviation in the quadrature operator x is going to be 1/2. Similarly, I urge you to do these calculations, very straightforward calculations. You can find out that the variance in the other quadrature y is going to be 1/4, and therefore standard deviation in y in the coherent state is going to be simply 1/2. And this is going to give you a very useful result, that the product of the uncertainty in the quadrature x and quadrature y is going to be 1/4, and this result is valid for, it is in the context of coherent state. Okay, for a coherent state, the product of the uncertainty or the standard deviation in the quadrature x and quadrature y is equal to 1/4. Okay, this is going to be very useful later on. To quickly summarize, what we have got is that expectation value of this quadrature operator x is real part of alpha. So this is alpha cos phi. Similarly, you can show that the expectation value of the other quadrature operator y is going to be mod alpha sin phi, and delta x, uncertainty in the quadrature, the standard deviation in x is equal to 1/2, uncertainty in the quadrature operator y is equal to 1/2. These results can be expressed through a plot, xy plot, and here you see you are getting a circle, and these equations for the expectation value of the quadrature operator x and quadrature operator y gives you an equation for a circle, and this circle is at a distance mod alpha from the origin, okay, and this angle is here phi, and width of the circle in x and y both is 1/2. Let me now quickly talk about vacuum state, and then you will see the importance of this particular plot. Now in the vacuum state, the expectation value of this quadrature operator x, so now I am going to talk about vacuum state, and you already know that in the vacuum state the number of photons in the state is equal to 0. So expectation value of quadrature operator x, you just have to find out this quantity, and it is very easy and straightforward to see that this is going to give you simply 0, right? And similarly, the expectation value of quadrature operator y is going to, again it's going to give you, because okay, let me write here first, because I'm going to calculate the quadrature operator in the vacuum state, and quadrature operator y is defined as a minus a dagger divided by 2y, and this is also going to give you 0. And you can now calculate x square in the vacuum state, and you will have to calculate this particular quantity, and if you do that, you are going to get 1/4 0 a plus a dagger, and a plus a dagger operating on get 0. This time you are not going to get 0, rather you are going to get this finite quantity 1/4. It implies thus we have the variance in x in the vacuum state, okay, that is going to be, again if you just have to put the values in this expression, and you are going to get 1/4. That means you are going to have delta x uncertainty in the quadrature operator x is equal to 1/2 in vacuum state, okay, and the same thing by the way you got even for coherent state. Similarly, you will get for the quadrature operator y, you are going to get this, already you know that expectation value of quadrature operator y in the vacuum state is 0, and delta y, the uncertainty is also you can calculate, and you are going to get it to be 1/2 for vacuum state. All right, so this you can again plot it in the xy diagram here, okay, this is what I have done for a vacuum state. But now what you see, now this circle is located at its center is located at 0. On the other hand, if you compare it with the xy plot for the coherent state, now you see it is displaced by an amount mod alpha from the origin. This is the reason why coherent state is referred to as the displaced vacuum state, and this has important consequence as we will see soon. By the way, this xy plot that we have done is also called phase space plot. The reason is very simple, because you know the position operator for a harmonic oscillator x cap can be written in terms of creation and annihilation operator as x 0 point fluctuation a plus a dagger, where x, this is called 0 point fluctuation, this distance is square root of h cross divided by twice m omega. If you have studied quantum mechanics of harmonic oscillator, then this must be familiar to you, and this is very important to remember also. And that the momentum operator is equal to I m omega x 0 point fluctuation a dagger minus a, okay. Now if we calculate the expectation value of the position operator in the coherent state, then you can very straight away calculate it, and this you are going to get it as x 0 point fluctuation alpha a plus a dagger alpha, and this already we have calculated. By the way, we know that we can write it in terms of the quadrature operator x as well. You have x 0 point fluctuation alpha x cap, okay, alpha, and this we have already calculated, and this is going to give you twice x 0 point fluctuation real part of alpha. Similarly, you can calculate the expectation value of the momentum operator in the coherent state, and that's going to be alpha p alpha, and p is already we know I am omega x 0 point fluctuation alpha here, and you will have a dagger minus a alpha, and if you do the calculation, okay, you can again write in terms of the quadrature operator y alpha y cap alpha, and this is going to give you twice m omega x 0 point fluctuation, and this is going to give you imaginary part of alpha. So you see that the real part of alpha is associated with the expectation value of the position operator as well as the expectation value of the quadrature operator x in the coherent state. Similarly, the imaginary part of alpha is associated with the expectation value of the momentum operator in the coherent state as well as expectation value of the quadrature operator y, and that's the reason xy quadrature plot is equivalent to the position momentum plot or the phase plot. I hope you get the idea. Now, as we have found that the coherent state is nothing but displaced vacuum state, which is also known as the vacuum state, as you know, is also known as the ground state. So coherent state is nothing but displaced vacuum or ground state. So let's discuss about the so-called displacement operator in this context. Say we have an arbitrary wave function psi of x, and this wave function is displaced by an amount delta x, resulting in the new wave function psi tilde of x. Okay, this new wave function psi tilde of x is equal to is the same as the old wave function at a distance. So this new wave function psi tilde x is equal to the old wave function psi at distance x minus delta x, where delta x is very small. Therefore we can apply the so-called Taylor series expansion, and then we are going to get terms like this, say psi of x minus delta x, delta psi of delta x, and so on. And these I can now write as 1 minus delta x plus, so there will be many terms, and I can write psi of x here. And if you look at this particular term, this is nothing but e to the power minus delta x psi of x. So this quantity, I can say that this is my displacement operator. So what I have is psi tilde of x is equal to, and displacement operator basically results in a new wave function when it is applied to the old wave function. So this is what I get. Now here the displacement is done only along the x direction, so let me discuss that first. So I have exponential minus delta x delta of x here, and we know that this momentum operator p, I can write it as minus I h bar delta x. So this will help me to write this displacement operator e to the power minus delta x delta x in terms of this momentum operator as e to the power p by I h bar delta x. This delta x is actually nothing but the value of the displacement along x direction, and it can be obtained by taking the expectation value of x in the coherent state. Also, we know that this momentum operator p is equal to I m omega in the context of harmonic oscillator, x 0 point fluctuation, a dagger minus a. Okay, and this will enable me to write p by I h bar. I'm just writing this term. Delta x is equal to m omega by h bar. Alright, then I have x 0 point fluctuation, delta x a dagger minus a. Okay, now we know that this x 0 point fluctuation is equal to square root of h cross divided by twice m omega, and this will enable me to write m omega by h bar is equal to 1 divided by twice of x square 0 point fluctuation. Okay, using this I can now write p by I h bar delta x is equal to 1 by twice x 0 point fluctuation delta x a dagger minus a, and therefore this way. Okay, by the way, you know this delta x, this is the uncertainty in the position, and that is equal to twice of the real part of alpha x 0 point fluctuation in the coherent state. We know this. So displacement operator, I can now write it as e to the power p by I h bar delta x. I can write it as e to the power real part of alpha a dagger minus a. Okay, now you can get actually similar expression for the almost similar expression for the displacement operator if the displacement is done along the momentum direction in the phase space. So this will enable us to write a general displacement operator as follows. So we can have d alpha is equal to, this is a general definition of the displacement operator combining both the displacement along the x and p in the phase space. So I have exponential alpha a dagger minus alpha star a. So this is the general definition of the displacement operator I have, and because of the fact that we have already learned that the as part of our analysis that this coherent state K alpha is nothing but the displaced ground state. So therefore if I apply this displacement operator in the ground state, I should be able to get a coherent state. So let me actually show you this by explicit calculations. First of all, let me first simplify the expression for this displacement operator using the so-called Campbell-Baker-Hausdorff identity. Using this identity, we can write this displacement operator in this particular form. And it's very easy to see here that this particular commutation relation is also satisfied if I take my a and b. Here I have taken, while I apply this identity, I have taken a as alpha a dagger and b I am taking as minus alpha star a, and you can see that this operator a and b which I have taken as alpha a dagger and minus alpha star a, this satisfy this particular commutation relation, and therefore I can apply this Campbell-Baker-Hausdorff identity, and using that identity I can write this displacement operator in this particular form. And now let me apply this displacement operator in this particular form to this vacuum state or the ground state, and if I apply this, then this is what I have here. You see e to the power minus half 1/2 mod alpha square is a constant quantity, so I'm taking it just out. And but this quantity in the middle is an operator, and this is also an operator. However, e to the power alpha a dagger, I can write it in this exponential. This exponential I can write in this form, because you know that e to the power x we can write it as summation n is equal to 0 to infinity x to the power n divided by n factorial. Utilizing this, I can similarly use this operator right in this particular form, and then it is this operator. In fact, I mean to say that this is the operator and this is applied to this ground state, and I'm now showing it how you can apply it. It is very easy. If I expand it, then first term would be k0, then the second term would be minus alpha a, which is then going to apply on the ground state k0, and so on. You will get higher order terms. But as you know, a dagger applied on the annihilation operator applied on the ground state is going to give you 0. Similarly, all the higher order terms will go to 0, then you will be left out only with k0, and therefore this term is going to give you k0, and from here you get this particular line step. And then you know that when this also I have already told you some time back, then utilizing this one you can get your when your displacement operator is applied on the ground state, ultimately you get this particular expression. And as you can see, this expression is nothing but it represents the so-called coherent state. So thereby we have shown you that when displacement operator is applied on the ground state, then you get the coherent state. That's the reason why coherent state can be referred to as a displaced ground state. Now, this displacement operator has many important properties, and these properties can be very easily proved because you know the form of this displacement operator. So you can easily prove these properties. Say d dagger alpha is equal to d of minus alpha, d dagger alpha d alpha is equal to d alpha d dagger alpha. This product is going to give you the identity operator. And if d dagger alpha a d alpha, if a is sandwiched between this two displacement operator d dagger alpha and d alpha, then you get a plus alpha. And similarly, if this annihilation operator is sandwiched between d dagger alpha and d alpha, you get a dagger plus alpha star. In fact, let me quickly show you one of these properties. Say for example, let us show this. To show this, we have to use the so-called Becker-Hausdorff formula, and the formula you may have seen it in quantum mechanics course also, in your quantum mechanics course, but it's very simple. This formula we can utilize. And okay, let me show you how we have utilized it. So d dagger alpha is this expression, because d alpha, you know, it is alpha e to the power alpha a dagger minus alpha star a. So d dagger alpha is going to be simply the complex conjugate of the whole thing. And now here what we are doing is that we are taking this quantity as a, right, and this quantity is my b, and this quantity is nothing but minus alpha star, this one I mean to say alpha star a minus alpha a dagger. So therefore taking, let me write once again here, a, I am taking a as alpha star a minus alpha a dagger, taking this and then applying this Hausdorff formula. Then I have first term would be your b is equal to a, this is what you get, and commutation between a and b is this, and then you will have higher order terms. First let me calculate the commutation between a and b. A I am taking it as a, this quantity, and b is here a, annihilation operator. Then you can easily get it to be this commutation relation will give you a constant alpha. Then d dagger alpha a d alpha, this one you can expand, and here you have this alpha. And then because you know this one, a commutation between A and B, so therefore you can also implement this term. So A is your this particular term, AB commutation is going to give you alpha, and as you can see this is a constant term, so therefore this commutation relation is going to give you 0, so therefore you will be left out with this expression which actually we wanted to show, and this is an important property of this displacement operator. One of the important issue related to coherent state is that coherent states are not orthogonal. Okay, let's show it quickly, because you know this is the expression for a coherent state. Then if I take a scalar product with another coherent state beta, and then you just follow this mathematics, very simple. You just have to put the ket beta expression here, and if you do that, then ultimately in the number state you are going to get mn, and this is going to give you delta mn, Kronecker delta mn. And using the property of the Kronecker delta mn, because Kronecker delta mn says that it is equal to 1 if m is equal to n, otherwise it is equal to 0 if m is not equal to n. So therefore utilizing this property, ultimately you can show that this is the expression you are going to obtain, and therefore beta, the scalar product of alpha and beta mod square, if you take it, then this is the expression you will get it, and therefore you can see that this is obviously not equal to 0. That means that two coherent states are not orthogonal. However, coherent states are complete, and actually it is also called overcomplete. I will come to that why it is called overcomplete. The completeness condition for coherent state is given by this expression. Okay, let us prove it. I have shown you the proof here. I'm just putting on the right hand side the expression for ket alpha, and then expression for the bra alpha, expression for ket alpha. I am now taking the summation from n is equal to 0 to infinity. For the bra alpha, I am taking the summation from m is equal to 0 to infinity. And then what I am doing, then this integration I am going to have. This integration is a double integration because alpha is a complex quantity. Being a complex quantity, it has two components, real part and the imaginary part. So that's the reason it's a double integral. However, we can actually simplify it very simply if we change to the so-called polar coordinate. So I am taking this area basically d2 alpha as r dr d theta, and while I am taking alpha is equal to r e to the power I theta, the mathematics is straightforward. Then you can just simplify this integral by taking alpha is equal to r e to the power I theta as I have taken here. So you can easily follow this. D2 alpha is r dr d theta, and alpha is equal to, you see what I have put is that alpha is equal to r e to the power I theta I put, and this will give me this one, this particular expression, and this integration from 0 to 2 pi e to the power I m minus n theta d theta is basically equal to 2 pi into delta nm, because this is basically the delta function. And applying this one, you can simplify this whole term. I can very easily just write it. This is the coming from the angular part, and this is coming from that radial part, and then I can radial part also I can simplify further. If I take r square is equal to epsilon, then 2r dr is equal to d epsilon, and if I put it here, then this expression is nothing but, actually this integral is nothing but n factorial. And utilizing this, you see n factorial will get cancelled out, and then you will be having this quantity, and this is nothing but the completeness condition for the the number state, and therefore you ultimately prove that completeness relation for the coherent state, and this coherent state is said to be complete, and it's also sometimes called overcomplete, because though it is complete, but the coherent states are not orthogonal to each other. Because of this non-orthogonality, it's called overcomplete. Now let us discuss about squeeze states. To discuss it, let us consider the ground state of a harmonic oscillator. So here I have plotted the harmonic potential, and this harmonic oscillator has the oscillator frequencies omega, and one can write the position operator and momentum operator of the harmonic oscillator in terms of creation and annihilation operator like this: x is equal to x in 0 point fluctuation into a plus a dagger, and similarly p is equal to I m omega x 0 point fluctuation a dagger minus a. Here this 0 point fluctuation x 0 point fluctuation is square root of h cross by twice m omega, and the ground state of the harmonic oscillator, as you know, it is the bell shape Gaussian. Now let us squeeze this ground state. That can be done by increasing the curvature of the potential, resulting in a new ground state and oscillator frequency omega tilde, and omega tilde is greater than omega. And in this new harmonic oscillator, similarly you can define the position and the momentum operator in terms of new annihilation operator b and b dagger for this new harmonic oscillator, and I will show you how this new creation and annihilation operator of this new Hamiltonian is related to the old one. Here b, let me emphasize, here b refers to the annihilation operator for this new harmonic oscillator, b dagger is the creation operator for the new harmonic oscillator, and the 0 point fluctuation x tilde 0 point fluctuation is defined as square root of h cross divided by twice m omega tilde. Both the harmonic oscillator has the same mass, but now their frequencies are different, and we are going to compare both of them. And if we compare them, comparing them, we will be able to find out how this new annihilation operator is related to the old annihilation operator. This annihilation operator b, using this equation, one can write by this expression b annihilation operator we can write as 1 divided by x tilde 0 point fluctuation, where x tilde 0 point fluctuation is the 0 point fluctuation in terms of distance for this new harmonic oscillator. We can write it at x plus I p by m omega tilde. Now x I can write in terms of the old creation and annihilation operator and old this 0 point fluctuation, x 0 point fluctuation like this. Similar is the case for the momentum operator. And then doing the maths, very simple algebra, you see x 0 point fluctuation divided by x tilde 0 point fluctuation is square root of omega tilde by omega, and putting all these quantities there, you can eventually find that this annihilation operator b, new annihilation operator b, is related to the annihilation and the creation operator for the old harmonic oscillator. This is what you get. Now if you take cos hyperbolic r as this quantity and cos hyperbolic r as this, sine hyperbolic r as this quantity, and you can take that, because you see, if you take cos hyperbolic r like this and sine hyperbolic r like this is going to satisfy these equations. Then you can write this annihilation operator for the new harmonic oscillator in terms of the creation and the annihilation operator for the old Hamiltonian by this expression. Now here the squeezing is done along the x direction only. In general, squeezing can be done along any direction in the phase space, and if you do that, then you can define a general expression for the new annihilation operator for the harmonic oscillator, and there is basically going to be a phase factor is going to come, that is e to the power I theta term would be there, and theta is equal to 0 refers to the fact that the squeezing is done along the x direction in the phase space, and this particular transformation is known as the Bogoliubov transformation. Now let us, having this annihilation operator with us, let us find out what is the variance of x in the ground state, and we can calculate it very easily. And if you do the calculations for this new harmonic oscillator, position operator expectation value in the ground state of the new harmonic oscillator can be easily worked out, because b is a annihilation operator. So quite clearly, because it is an annihilation operator, when it operates on the ground state, it is going to give you 0. And using all these things, so you can find out that the expectation value of the position operator for the new harmonic oscillator in the ground state is 0, and similarly you can find out x square, expectation value of x square for this new harmonic oscillator in the ground state. That is going to be simply h cross divided by twice m omega tilde. This is what you are going to get for x square as the expectation value of x square. So the variance of this new harmonic oscillator for the position is simply given by h cross by twice m omega tilde. Similarly, you can calculate the variance for position for the whole harmonic oscillator is going to be h cross divided by twice m omega. And if you compare both of them, if you take the ratio for the variance for the new harmonic oscillator and the old one, then you see that the variance for the new harmonic oscillator is less than that of the old harmonic oscillator. It also means that the position uncertainty for the new harmonic oscillator is less than that of the position uncertainty of the old harmonic oscillator. As you know that the position operator is associated with the x quadrature, it also implies that the uncertainty in the x quadrature for the new harmonic oscillator is less than that of the old harmonic oscillator. This means that the x quadrature is now getting squeezed. In fact, you can calculate the momentum variance also, and if you do the calculation, you will find that the momentum variance for the new harmonic oscillator is going to be given by this expression, which is equal to h cross m omega tilde by 2. And if you compare that with the old harmonic oscillator, you can see that the old harmonic oscillator has a variance which is less than that of the new harmonic oscillator. That means the momentum uncertainty in the new harmonic oscillator is greater than that of the old one. And effectively it also means, because the momentum operator is associated with the y quadrature, that the uncertainty in the y quadrature for the new harmonic oscillator is greater than that of the old harmonic oscillator. So what you have seen is that because of the squeezing, one quadrature is getting squeezed at the cost of expansion of the other quadrature. Now what about the product of the variances? And it can be very easily seen that the product of the variances in the position and the momentum for the new oscillator is going to be given by s cross by 2 whole square, and that will going to give you the product of the uncertainty in the position and momentum for the new harmonic oscillator, that is going to be equal to simply h cross by 2, which refers to the so-called minimum uncertainty product. And in terms of the quadrature, the uncertainty in the quadrature x and y is equal to 1 by 4, which refers to the minimum uncertainty product, as I have said. In fact, for the case of the old harmonic oscillator also, the product of the quadrature is equal to 1 by 4. So because of the squeezing, the product of the uncertainties is not going to change, and this can be very nicely represented by this phase plot. Here you see this is the case for the squeeze vacuum state. Now in the case of the vacuum state, the plot, basically the phase plot, gives a circle, and because of the squeezing, as you have seen, that the x quadrature is now getting decreased and y quadrature is now getting increased. So this is what it is shown here in the plot. However, the product remains equal to 1 by 4. And if you compare that with the case of the coherent state, in the case of the coherent state, both the uncertainty in the x quadrature and y quadrature were equal, and that were equal to half. But in the case of the squeeze state, quadratures are either the x quadrature is less than half and y quadrature is uncertainty in y quadrature is greater than half, right? Or you can also have a situation where the x quadrature is enhanced but y quadrature is getting squeezed. However, the product is still going to remain the same. Minimum uncertainty product is maintained. This is the reason why coherent state and squeeze states are known as the Gaussian state, because Gaussian state has the minimum uncertainty. Product of the uncertainty is minimum for the Gaussian states. Now the question is there a squeezing operator just like the displacement operator in the case of coherent state? The answer is yes. We do have a squeezing operator, and this squeezing operator for a single mode is given by this expression here, and xi is a complex number here, quantity, and we can get the squeeze state by applying this is actually squeeze vacuum state represented by k xi, and it can be obtained by applying the squeezing operator on the vacuum state, that means k0. And this squeezing operator is actually nothing but the time evolution operator with the appropriate Hamiltonian, and here the squeezing Hamiltonian is given by this expression. And in fact, as I said, that B is the annihilation operator, and it is actually time evol annihilation operator, and so quite often we can write B is equal to A of t, and in terms of this A of t annihilation operator, time evol annihilation operator, the squeezing operator can be expressed in this particular form. On the other hand, the squeezing Hamiltonian, which should be more clear to you in the problem solving session that we are going to discuss in the next class, this can also be written in this particular form. Here, why this form is useful, because you see here h cross omega gives the energy of the oscillator, harmonic oscillator, and here z is a free parameter, and xi is taken to be omega z. Okay, and then in that case, if I take xi is equal to omega z, then I can write this squeezing Hamiltonian in this particular form as well. In the next class, which will be a, as I said, problem solving session, I will show you that indeed this Hamiltonian does the job of squeezing. The squeezing operator also has several useful properties. Some of the properties I have listed here. These are the properties. And let me very quickly take you through the steps to show you a proof of one of these properties, say this one. Let me show you how to get this. And to do that, you just have to apply the so-called Hausdorff-Becker formula, and okay, and you have to work the things term by term, and then it would be very simple. And here I have written this S dagger xi, and here S xi, and B I have taken to be A, annihilation operator, and A is taken to be this quantity. And then if I put it in the Hausdorff formula, I have to work the things term by term. First, let me work out this commutator, then next one is this, and this. Thirdly, I will calculate this commutator, and this will give me an idea about the series, and I will see whether I can get some nice relation out of it. In fact, if we calculate the commutation A and B, and A is taken to be this and B is A, and if you do the operator algebra, very simple and straightforward, then this is what you are going to get. Similarly, if you do the second commutation, if you calculate it, because already you have AB is found to be minus xi A dagger, so calculations become then simple. And if you do this, then you are going to find this result, and then you can find out the third commutation relation, and that's going to give you this expression, this result, and then you clap all the terms together, and this is going to give you the expression, this expression. That means your S dagger AS, this is what you are going to get. Then you are taking xi is equal to r e to the power I theta, and if you put it here in this expression, then you are going to finally obtain this result, and which is one of the very important properties for squeezing operator.
Let me stop here for today. In this lecture, we have discussed about coherent states of light and squeeze states of light. Actually, squeezed states of light I have discussed in the context of a general harmonic oscillator. However, this discussion is valid for even squeezed states of light as well, because you know that when quantized light behaves like a harmonic oscillator. In the next lecture, which is going to be a problem solving session, as I have already told you, we are going to solve some problems on squeeze states, and this is going to clarify many of the concepts of squeeze states. So see you in the next lecture. Thank you so much.